There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal-rich.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. It'll take a number of years to get there.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
We'll go into 4 concentrically smaller orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma-ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
We're using a particular thruster technology, Hall effect thruster technology. They operate 5 times more efficiently than normal rockets, so they use a lot less fuel, and is what allows us to get into orbit around this asteroid.
Solar electric propulsion has been around for quite a while, and it has flown before, but we're continuing to push the boundaries. We're going to have big 5-panel fold-out solar panels that will provide the electricity for the thrusters, which use as propellant the noble gas xenon.
This will be the first time that Hall effect thrusters have flown in deep space.
Studying the evolution of a planetary body is a detective story.
There's a magic to when you actually are on the launch pad and you say, we're go for launch.
And you feel like singing and dancing and you feel like throwing up at the same time.
Let's go discover things about our solar system that we have no other way to do. I think that it's fundamental to who we are and also who we should be. It's an incredible opportunity to be a part of the team making that happen.
All right, so that was very good to get that. To get that up there. That was good to get that up there because they were going to have to do a condensed version, but now you kind of got the outline, right? So thanks very much for coming to the talk today. I really appreciate it. Very important caveat that I'm going to repeat through the talk. This is artwork done by fabulous Hollywood artist Peter Rubin, who's also done things like he designed one of the S's for Superman, and he worked on Ghostbusters. You get in the drift. This is art, right? This is not a picture. This is his interpretation of my description of what we imagine and hypothesize the science to be. We used to Zoom together on weekends for like a year while he did this art. Probably it's going to be totally different than everything I tell you today. And that's one of the things that's fun about it. All right, so as humans, we've sent people to rocky bodies like the moon and robots elsewhere. This is the Orientale Basin. It's a big impact basin on the limb of the moon. Chip, is this one of your favorite basins? I think it's so gorgeous. I think it's the best one. Here's Burns Cliff on Mars, another rocky body that we visited with robots and continue to visit. And we've been to great big ice and gas giants. This is Jupiter's great red spot, and then here's an icy moon. But what we haven't ever done is visited a body that seems to have a metallic surface. And we think that Psyche has a metallic surface, as explained in that little trailer video. Again, this is just artwork, But I think that is the most compelling thing about the whole deal, because there aren't many classes of objects that humans have never visited. And so we're going to discover something entirely new and surprising, because we discover totally new and surprising things that outdo our sense of curiosity no matter where we go in the solar system. And here we're going where all we have is wild guesses. All right, so what does it actually look like? Since I'm being clear with you that we don't know, that's what it actually looks like. That's what it looks like from my backyard. The red circle around the little asteroidal dot, which is just what those early discoverers were discovering. And we have no pictures of it, but we have shape models. So these shape models, and because we have astronomers here, I'm just going to add this. This is a figure from Shepard et al. 2021. And you can see there are 3 generations of shape models, 2 of which belong to Shepard, and then there's a third one. And he's pointing out that they are kind of in agreement. And they do it by looking at observations acquired at a wide range of wavelengths. Arecibo, S-band delayed Doppler imaging. Arecibo does not exist anymore. That's very sad. The Atacama Large Millimeter Array, plane of sky imaging, adaptive optics from Keck and the Very Large Telescope, and also stellar occultations where they watch the stars and the apparent path of the asteroid intersect. And so by looking at the way light and radar reflect off this spinning object, they can actually see how the reflected light in radar coming back changes, and knowing how fast it's spinning, they can make a shape model of the object. So this is the best that we know, but it's also misleading because there are other shape models done by also excellent groups that don't look like this. And so we think it's kind of a potato, but that also, potatoes can be lots of shapes, can't they? So here's one of our best shape models for Psyche on the left, and here's Vesta, recently visited by the Dawn mission. And then there's Eros, which I like to show, also visited by NASA missions. And Eros and Psyche, of course, are the mythological couple, which is kind of fun. There is also another asteroid that has recently been visited on the screen right now. I don't know if you can see it. It's right there. That's how big Bennu is in comparison to these others. I think a lot of us, including myself, tend to sort of think of asteroids like we are in Star Wars or Star Trek, and we can just like zoom in between the asteroids, and they're all more or less the same size and the same stuff. And so it's good just to remember that they represent the building blocks of the planets, and they're very different from one another, both in size and composition. So visiting a new one means discovering a whole new kind of world, really. All right, so recognize this beautiful relief map of where we are. I want to show you how big Psyche is. Psyche is this big. And so perhaps not giant compared to a state, but for an asteroid, it's very big. And even though there's well over 1 million asteroids known in the main belt of in the main asteroid belt, Psyche has something like 1% of the mass. So it's large and dense, large and dense. So what do we think it is, large and dense? I think this is the only data I'm showing. And I know that not everyone watching and listening today is a scientist, but I know that you hate to be condescended to no matter who you are. So let me walk you through this chart. I think it's super interesting. And it's the first way that we think about what Psyche's made of. All right, let's look at the vertical axis first. It's density in kilograms per cubic meter. And when you look at this density axis over here, you see that there are 3 red lines that intersect it. The top one says camosite. That's an iron-nickel metal mineral that comes from meteorites that we think is most likely more or less the composition of the metal part of Psyche. You see, it's about 7,000, it's more than 7,000 kilograms per cubic meter in density. Next down is troilite, that's iron sulfide, which we also expect to find on Psyche. And then at the bottom, enstatite, which is a rock-forming silicate mineral like you might find in a rock outdoors. And so rock, this is what you should be taking home if this is not your world. Rock, about 3,000 kilograms per cubic meter. Metal, more than twice as dense. And so by plotting the densities of the asteroids, you can see at a glance probably how much metal or rock they might have in them. That might be an example of what we're fighting with the interference. So then the horizontal axis here is the year of publication of people's estimates of the density of Psyche. And my favorite data point, of course, is that one around the year 2000 at 11,000 kilograms per cubic meter, which if you are a scientist in this field, there's literally no material that could be. And so I've got to look back and see what they really thought it was. It would have been super exciting because it would have been actually a brand new kind of material. And then you could see how the density estimates kind of funneled down. And then we were selected for flight in here And after that, people have been pretty clear that Psyche is around 4,000 kilograms per cubic meter. And so that would mean it's a mixture between rock and metal. But it's actually quite outstanding. Right at this moment, here are 4 other asteroids. Cleopatra is a metal asteroid. There's only about 9 asteroids that are thought to be made of metal. And so at the moment, you know, these things change as people get better data. At the moment, Psyche is the densest asteroid known. And most asteroids plot down here in this gray field, meaning that they are void space and ice and a little bit of rock. Psyche could be pure metal plus void space, you know, space fractures filled with the vacuum of space. Or it could be a mixture of rock and metal. Or it could be a mixture of something that's not rock, like carbon and metal. We don't know. But that's the first line of evidence that says Psyche has got a big metal component. All right. You who study meteorites are going to look at this and go, this is nuts. So one of the things we've tried to do is compare the spectra, the reflected light spectra off of Psyche, with the reflected light spectra off of meteorite samples. You may know that virtually all the meteorites we have on Earth are recent transients from the asteroid belt. They were knocked off of asteroids, except for the super special ones that came from Mars or the Moon. Almost all of them come right from the asteroid belt in fairly short order. So they're good examples. They're sort of a compositional library that we can use to compare to Psyche. Psyche's spectra matches meteoritic metal, like that camosite, and troilite. And it matches these bizarre meteorites called CB chondrites. And if you look at the one on the left, the gray is iron nickel metal. Don't they look like bubbles? Like they're all pretty round, right? So we think that they were liquid and they froze as droplets. And in between them is the darker material, which is silicate rock. And I'm going to mention this for those of you who are specialists because it's so interesting and strange. The spectra from Psyche indicates that the silicate rock component, or whatever is not metal on Psyche, has almost no iron oxide in it. This is a very rare thing. If you pick up a rock on Earth or Mars or Venus or the Moon or Mercury, you would find minerals in there that have both magnesium and iron oxide in them, and they have a very distinctive spectra. Psyche does not have that. And so that's an interesting thing about this meteorite, is that those rock bits between the metal spheres have very little iron oxide. So this is the kind of sleuthing we're doing from a distance to try to figure it out. So again, let me say, we do not know what it is. Does not really make sense for it to be a giant CB chondrite. So we'll find out. But this is basically how we think that planets are made in a super simplistic way. We start with a spinning disk of gas, dust, and pebbles over at the left. And then it used to be when I showed a slide like this, I had an asterisk right there between that and planetesimals. And I would say that's the international scientific symbol for, and then a miracle occurs. Because for a long time, people had no plausible physical way to get from dust and gas to these tiny planets, planetesimals, the size of continents or big cities or even maybe the size of the moon. There wasn't a plausible physical pathway. Now there's lots of good ways that people think it could happen. It's really kind of cool. So I took the asterisk out. So they clump together into what are called planetary embryos, things like the size of Mars, and then finally up into planets. And so we think that Psyche is a little part of one of those planetesimals. Maybe it got its rock knocked off, like we were talking about in the video. So the data right now says that it took only 5 million years to make Mars. And the number that I always joke, I used to tell my students they fail if they don't remember 4.568 billion years ago, because that's the age of the first pebbles that formed in our planet, in our disk. So like the first solids in our solar system, 4.568 billion years ago. Only 5 million years after that, we had Mars. Earth may have formed as fast or faster, but the giant impact that created our moon happened about 100 million years later. So if our solar system was 24 hours long instead of 4.568 billion, Mars was made in 94 seconds, and the planetesimals were made in 20 to 30 seconds. So they are remnants of the very earliest part of the solar system. So these are stills from that beautiful little video that was actually a flip book that we gave to our reviewers because we wanted them to understand our vision in our heads of the process of making Psyche. Because without knowing that little video that you just saw, where it goes like this, and then it goes like this, and then it goes like this, you wouldn't understand why we even chose the instruments that we did. So we made flip books for them, and Peter Rubin, again, did this artwork. So now we're imagining that Psyche is mostly a stripped metal core with just a little rock on the outside, and that its convecting interior metal is making a magnetic dynamo, the same way our Earth makes a magnetic dynamo. And we hope that maybe it happened this way, because if it did, then the metal on the outside is freezing into that lid while the inside is still making a dynamo, and that metal could hold onto the magnetic field for us to go and measure in 2029, which is the actual date that we're getting there. And you see this yellow squirting out. There's a wonderful process of core formation whereby the metal liquid immediately separates into two liquids like oil and vinegar, only it's not oil and vinegar. It's boiling hot liquid iron and iron and sulfur. And so that iron and sulfur immiscible liquid is buoyant and could squirt out. So these are hypotheses we've had for years. Who knows what we're going to see? I can only just pretty much say it won't be this, even though this is our best guess. So today it might look like this with just little regions of magnetic field, and our spacecraft will go around and go in and out of those magnetic field lines. We hope. Wouldn't that be great? But who knows? So where is Psyche? There are the asteroids in purple, and there's Psyche's orbit way in the outer main belt between Mars and Jupiter. How many of you have seen one of these fabulous headlines about how Psyche is the asteroid that's going to make everyone on Earth a billionaire? Did anybody see that? You've seen them. A couple of people have seen them. And I hope that you understand. So this was like really people got very excited. There have been literally hundreds and hundreds of these stories, including in Forbes magazine. And so, dare I tell you all the ways that this is wrong. And I'd like to talk about it here because look how far away this thing is. We're not even taking a sample ourselves. We have zero technology to bring this asteroid back to Earth. It probably would be a gigantic catastrophic error if we tried. And imagine that we did. Imagine we could bring Psyche back. Would it be worth anything? No, because talk about a surplus on the market. You would crash the whole metals market, and all of your work would be for naught. And so there are at least 15 ways in which this idea that this asteroid is worth all this money is a fallacy. But the guy who writes for the Space News on Forbes told me that he still likes to at least mention it while he disproves it because it gets so many people's attention. Put a dollar sign in front of it, they're pretty excited. Anyway, Psyche's far away, you're not bringing it back. And it is never going to hit the Earth. It's not Earth crossing. So we've got 3 science goals. Understand previously unexplored building blocks of planetary formation, that is the iron bodies. Look inside terrestrial bodies by looking at cores the only way we ever can. And explore a new kind of world. Just explore something new. What does a metal surface look like? We have no idea. Objective A, we have 5 science objectives. I know that you won't be surprised to know that NASA has a very highly structured way that you're meant to propose and carry out a mission. And one of the reasons for that is you want to have science goals that you can actually attain with the instruments that you're going to fly. You need to know what those questions are and be pretty sure that you know how to answer them. And so our first of our 5 big questions is determine whether Psyche is a core or is it something else. And so we write this as unmelted material because one idea would be maybe Psyche is material that formed very near the sun where it was extremely hot and irradiated, and that heat and irradiation reduced the iron oxide to iron metal in the materials of Psyche. I would argue, and maybe somebody can come up with a very unusual meteorite sample to prove me wrong. I'd argue that we have no samples of a material like this, but it's theoretically possible. And so this is just to say, this is the kind of world we're in, trying to figure out what Psyche is based on the data we have right now. Psyche itself is an improbable object. It's the largest of the very dense, apparently metal-bearing asteroids. And there's more data that I didn't show you, of course. But some of the data is contradictory. And so right at this moment, we really do not know what it is. And I think that's kind of great because it gives me this lovely luxury in science of having no ego-born determination that I want to prove a certain thing to be right. Because I don't have a hypothesis about this to prove. We have lots of ideas about how to test these questions, but we're all going to find out together. So I'm reinforcing again that we don't know what it is. So how does a NASA mission happen? Well, for me, it started with this paper that I wrote with Ben Weiss, who's now the deputy principal investigator of the mission, and Maria Zuber, who's the vice president for research at MIT, and is also the lead of our gravity science investigation on the mission. So we're all on it together. We wrote this paper back in 2011, and it was Does it sound like, for those of you who do not study meteorites, does this title, Chondrites as Samples of Differentiated Planetesimals, immediately cause a surge of rage and indignation in you? Does it fill you with like anger and a wish for retribution? Well, you're in the wrong field, because that's what happened to us. People thought this was a really horrible idea, and it was. I'd like to tell this story just because it super amused me and scared me at the time, and now it just amuses me. But I was junior faculty at LPSC when Ben gave his paired paper where he did the measurements of Allende. I'm not going to tell you the whole story; it takes too much time. And I gave the models. And it was at the Lunar Planetary Science Conference, and I'm getting up from my seat because I'm the next speaker. The room is totally filled for our talks, and like there's standing room only, there's people standing around the sides. And I'm walking up toward the podium, and before I even reach the podium, people are lined up at the microphones to rebut me. I hadn't even started talking yet. And so that was the only time in my life that ever happened. And it was kind of fun, and we all had great conversations, and some people agree with us and some people don't. But what happened was, two guys from Jet Propulsion Laboratory, two scientists, wrote me an email and said, "We really liked your paper. Do you want to try to propose a space mission to test your hypothesis?" And that is how this started back in 2011. I was working at Carnegie Institution for Science at the time, and we started working on it, and it took us a little while to even decide where we wanted to go to test the formation of planetesimals. And after about 6 months, we decided it was Psyche. And then 3 years later, we handed in our step 1 proposal in the NASA proposal system. Now, I'm sure many of you know that NASA has many different sizes of missions that they fly in planetary science. The really big ones, like the Mars rovers and Europa Clipper, that kind of thing, those are called flagship missions. And they are conceived of and run, really managed out of headquarters. And then there are competed missions, of which there are a number of different classes. The one that we competed in is called Discovery Class, and those are led by scientists. They're led by principal investigators, which in this case was me. And so my job is to, get the mission manager, which in this case was JPL, and our industry partner, which ended up being Maxar, and then all the other partners around the world, and all the science team, and like trying to get everybody to work together to do this thing. So we wrote this 218-page step 1 proposal with about 40 people, and we competed against 27 other proposals. And to my undying astonishment, we were selected to go into step 2, cover art by Peter Rubin. Recognize what this is? This is the moment of impact between two planetesimals that might strip some of the rock off one of them. So we're always trying to tell our story, telling our story. Step 2 proposal. This is like 30 seconds later with the impactor screaming off to the side and some of the liquid iron metal core showing underneath the rock that's being stripped away. This was a 1,000-page proposal. That we wrote over the course of a year with a team of 150 people. And that's not even the only thing you do in that competition year. It really was insane, and I could talk to you about it at length if you want to hear all about like a thing that is like 7 times your PhD qualifying exam, enacted as a Hollywood super production. That's like what these site visits are like. And so one of the things that happens at the site visit is you get encrypted emails from the review board asking you questions about your mission proposal. And at first, David O., who you saw on the mission trailer, our lead systems engineer, he and I were like, oh my gosh, but then we have a whole week to answer them, no problem. And then I realized these are the questions from experts that were not answered in 1,500 pages of previous documentation. And in fact, we ended up actually doing new space physics during lunch break to answer questions that end up being published, like stuff like that. It was really intense, super fun. We were selected, oh my God. So that morning in January of 2017, I've told this story in like a blog and things like that if you want to read about it. It was a kind of a funny moment getting a call from Thomas Zurbuchen saying we were selected. I had become completely sanguine through the great counseling efforts of my husband because I felt responsible for everybody, including, oh my gosh, the team at Maxar. They were trying to become a NASA prime contractor for the first time ever. All these people who'd spent so much time and money trying to make this happen. And I was just ready to hear no, and it was cool. And then we figured out if we were going to do it again. And he calls up and he goes, "You're going to be glad I woke you up this morning," he said, because he knew right away I'd been asleep, which was embarrassing. And he said, "We were selected for flight. But," and the very first thing he said was, "I need you to completely redo your student collaborations. I want to do something much bolder with your mission." So we came back with 10 different ideas from a new, bolder version of student collaborations. We ended up choosing 4. We do undergraduate, senior, capstone programs. University of New Mexico is not a capstone partner of the Psyche mission, so I'm here to invite you to become a partner with us in capstones if you want. We get real problems from the mission, from members of the mission who want real things solved, and they go out to student teams, and we try to get the teams to be interdisciplinary, not like electrical engineers working with chemical engineers, because that's like not actually interdisciplinary, but to have a student project manager and somebody who does marketing and someone who does budgeting and someone who does UX, UI, and someone who does coding, and like everybody you actually need, like you'd work with in the real life to do this. We have free online courses, one on the evolution and timeline of a NASA mission, one on how to put together inclusive teams, taught by a super expert, not myself, on this topic. And we have one coming on the debugging mindset and another one on the small bodies in the solar system, free to everyone in the world. We have got this great art program. We do it competitively. Undergraduates in all American 2- and 4-year colleges in any major, working in any media, are welcome to propose every year, and we choose 16 artists, and we fund them to produce original art. And it is so cool, and you can see it on our website, which is there, psyche.asu.edu. We get, graphical art. Someone was a jewelry maker. This guy was a ceramicist. You see that glaze? That glaze is a mixture of iron filings and thermite, which is an explosive. And he put it in his kiln, and it made this amazing texture. I learned about it afterwards, which was good. We've had cooks, like everybody, so you're welcome to join. We have had over 1,500 undergraduates in 6 years participate with us, including 1,300 in our capstone programs at 58 colleges and universities in 24 states and Puerto Rico. And I'm really proud of this program and really glad that NASA could fund us to do it, and it's just a joy every day. So, who are we? We are, as I was saying, ASU, JPL, Maxar is our industry partner. The Johns Hopkins Applied Physics Laboratory, led by David Lawrence, is making our gamma ray and neutron spectrometer. Malin Space Science Systems, ASU, led by Jim Bell, is running our imagers. And our magnetometers come from Danish Technical University. The gravity experiment relies just on Doppler radio with the high-gain antenna. That's being led by Maria Zuber at MIT. This is a big project. And at peak, we've had 800 people on the team. Right now, I think it's a little bit hard to count because we have people in so many different places, and there are teams that, at APL, how many people are really counted as a part of the team and who is just, it's hard to count. But I think we're at about 350 people right now. And the total budget of the project is over $1 billion. And so there's a lot of pressure and a lot of responsibility to make this happen. There's our 3 instruments that I was just mentioning. There's actually 2 magnetometers and 2 imagers that you saw on the video, right? And the beautiful gamma ray and neutron spectrometer. And today, one of my great moments today was actually having Rich really explain to me how cosmic rays get to be as energetic as they are, because I've never understood that physics. But it's cosmic rays that hit the surface of poor, naked, airless Psyche and cause those atoms on the surface that are struck by the cosmic rays to release gamma rays, which we measure with our gamma ray spectrometer, that tell us the identity of that exact type of atom. That's how we get the composition of the surface. We get the composition because the body gets struck by cosmic rays that come from the shock waves in the front of supernova explosions in other galaxies. Isn't that cool? Does that not pull together these 2 departments? I think that's kind of great. So here's how big it is. It's a big spacecraft. You see we've got these booms up on the top, and we're actually lifting our instruments away from the main body of the spacecraft so that the spacecraft itself doesn't interfere with the measurements. And I've had people ask me, well, if you put your science instruments way on the outside, like what the heck is inside this giant box? You might not know that the Mars rovers, when they get packed into their boxes, their equipment is so tightly packed that you can't slip paper in between it. And we've got mostly space inside this box, electronics, and a giant tank of xenon. But the reason that it's bigger than we need it is because we bought a more or less off-the-shelf model from Maxar Technologies, because they built over 100 Earth-orbiting communication satellites that use exactly this power system. So that's why we chose them. They could give us a firm fixed price. They knew exactly what it was going to cost to build this thing, and they saved us a lot of money. And it doesn't really matter. We launched some extra space, empty space, into space. So the other thing I want to mention over here, DSOC, D-S-O-C, the Deep Space Optical Comm. That is a technology demonstration that we're flying on behalf of NASA to test the technology in space. This amazing, oh my gosh, if we have time and questions and you're interested, I could like geek out on the tech here. But what it's doing is communicating with Earth using lasers instead of radio waves. Turns out you can encode a lot more information in a laser than a radio wave. So we joke that in the future, this is how we're going to get Netflix on Mars. So as we're going, we'll be testing this, and you can watch, this is going to be tested as we're flying through our cruise. When we unfold those beautiful solar arrays about the size of a singles tennis court, and here at Earth, it's 20 kilowatts of electrical power. And then because flux is a 1/r² relationship, the further you go away from the sun, the flux goes down as 1 over the radius squared. And since Psyche is out at 3.2, 3.2 squared is kind of like 10. So at Psyche, you get 1/10, about 1/10 of the power that you would here at Earth. And so that's not much. You can either run a hairdryer or you can run our whole spacecraft. Propulsion, coal gas thrusters, all the instruments, the works. It's just amazing to design that. We are going to launch on a SpaceX Falcon Heavy. And so they're going to re-land the side boosters with the biggest sonic boom you'll ever hear in your life. Because I'm going to sit on console for that launch, and a bunch of us got to go and sit on console for the launch back in November. And as soon as the Falcon Heavy left the launch pad, we all ran out of mission control into the parking lot to watch the boosters land like 3/4 of a mile away. And they came down through the morning fog bank. You couldn't see them at all. And suddenly you could see them. They get into the open air in the morning in Florida, just under the fog bank. And they snap on their engines so that they can slow down and land properly. And there's this vast sonic boom. And I actually shrieked a little bit, which isn't totally like me because it was just so loud. And one car alarm went off, and it was a Tesla. So I thought that was hilarious. I'm not even making that up. Yeah. But wait, as you heard in the video, we were supposed to launch in August last year. And by having this time curtailed, what you're actually being spared is like having me cry for a while because it was so hard to go through the slip. It is a huge deal to slip a mission. It's vastly expensive. And there has to be a long review with a big professional board who just grill you mercilessly to find out all the things that went wrong. We were a bit surprised. We did not know the thing that was going wrong until it was too late to fix it, even though the team is so awesome. But let me just say, a team that can build a complete, fully functional spacecraft and deliver it to Kennedy during COVID, 100% during COVID, they are miracle workers. And I support these people like to the ends of the earth. And the bit that didn't quite get finished was mostly in the software. But we got continued to go through this exciting day called a continuation termination review, at the end of which everyone votes, continue or terminate. And you can imagine, like, been working on it for 12 years, expecting it to be the bigger part of my career, hundreds and hundreds and hundreds of people and a ton of money. Like, there's a lot of pressure when that happens. And so last year was not the highlight of my life. I'm really kind of hoping this year's going to be a better year. And the team's doing great. So we are now launching in October of 2023, October 5th. Please put it in your diary. And keep your fingers crossed, both hands from now till then. I don't care if it hurts. I need you to do this. I think we're going to make it. October 5th, 2023. Then we're going to zoom around and get a Mars Gravity Assist in May of 2026. And then finally, we're going to head out to Psyche capture in August of 2029. So yeah, I think that's it for that. So it's almost 6 years. It was going to be 3.4. Psyche's in a little more awkward place. But it turns out it's actually in a better place for science. Because an interesting thing about Psyche is that the Earth and the other planets, for the most part, our spin axis is perpendicular to the plane of our orbit, or kind of close, like tilted. Psyche's is knocked right over into the plane of orbit, so it's like a rotisserie chicken. So you could imagine that. That's just a good image. It totally brings it to mind what Psyche is, but like a rotisserie potato, maybe. So for a quarter of the year, its north pole faces the sun, and its south pole is freezing cold nonstop. And then it gets kind of sideways to the sun, and the whole of Psyche is illuminated as it spins. Can you picture that? So we have better lighting conditions with this arrival. So it actually helps the science in that way. So as you saw in the video, we're going to step down. We're going to get all this data. We're going to get closer and closer as we better determine the gravity field and can calculate stable orbits as we go down. So a couple words about the importance of teams. Here I am with just a little part of our giant team. Something that has actually been the biggest driving force for me in my work is to try to find teams of people where the sum of the whole is bigger than the parts, where people are actually supporting each other to do better. And I think a lot of times in any high-stakes world, knowledge, money, whatever it is, you have people who kind of act like they own the city-state, and they're not always supportive of everybody, and it's easy to feel like you're being bullied out, or it's just not a supportive environment. We tried really hard not to make it that way, not just because it is ethically the right thing to do, but because it's literally a way to buy down risk. Why positive team culture matters. You make better decisions. More ideas are heard, cooler heads think better. Project risk is thus reduced. If you can have everybody willing to speak up, we had this motto, best news is bad news brought early. And you can imagine how this kind of hurts me even to say it, because it didn't work, right? I would say 70, 80% of the team, it really worked. The person with the authentic boots on the ground knowledge was the one who was asked to answer the question, not their manager's manager whose voice wanted to be heard. And when someone knew something was wrong, they knew that they would not be punished for telling that. That's what you need. You need the person with the soldering iron in their hand to say, I don't think this chip works. To have the courage and knowledge they'll be supported. Otherwise, you won't find out till after you launch. In a little part of the team, it didn't work. And it breaks my heart that that's true, but it's a big learning, Also, attraction and retention of talent. It turns out, however it is that you think of yourself, like however you identify yourself, if there's fewer than about 30% of people who are that same way in your group, you feel like you're alone. This is sociology science. And so if you do feel like you're alone, because you're in a group where there isn't a lot of you, it's much easier to feel vulnerable. If you don't feel like you're going to rise on your merits and be respected regardless of whatever it is that you look like or act like, you're going to feel vulnerable. So it doesn't matter what your hiring rubric looks like, you will not have a diverse team. So just trying really hard to make it possible for people to rise on their merits and for every voice to be heard, I think is a huge ethical and quality imperative. So I just had to proselytize for a minute. So let's see the spacecraft. So this is a spacecraft shipping container for a big spacecraft. This is Maxar's one. I have a great story about the one that we subsequently bought that I'd be happy to tell you later. The spacecraft is held up in there, and it's actually a self-enclosed clean room, absolutely sealed, very low particulate, and it's instrumented to everything, to pressure and shock and acceleration and vibration and temperature, and it has 2 generators in case one fails, and that's how this thing gets trucked around. So that's and to my alarm, I was like telling this story. There's a stencil just past those guys on the shipping container that says, "Space flight hardware do not drop." Which I still wonder, like, how was it even possible to drop it? And how would you not know what it was? I don't know. So the spacecraft chassis arrives at JPL in March of 2021. Here they are in the one of the 2 giant high bay clean rooms at JPL. And just feeling so excited. This is me and Henry Stone, our project manager, feeling so proud that week because there's our spacecraft all ready to be assembled at JPL with all of the science instruments and the software and the computer brain and all the rest of it. And going into the clean room isn't something I indulge in very often because I'm not building the spacecraft and I just disturb people. So unless there's something I need to see or a tour, I don't go. But going in is also just a weird thrill. You have to put on all this special equipment, and you have to put an electrically conductive band and this wire, which you could see, I could see it in a subsequent thing, and you have to plug it into the wall and degauss yourself so you have no static electricity in your clothing. Then you go into a little thing the size of a phone booth that is just filled with air nozzles, and it blows air all over you and sucks it out the top to get any extra particles on you. It's called the air shower. And they at first I thought they were mocking me, but they instructed me to put my hands up and dance in a circle. And so 1 by 1 or 2 by 2, you go in the air shower and dance in a circle, and then it's like an incantation. Then you're allowed to see the spacecraft. So that's what that is. So here's the great team that just finished installing the Deep Space Optical Comm. Very excited about this laser comm. Here's a hero shot. That was supposed to be 1 year to launch, right? Didn't happen. Still a hero shot, kind of nice. There's the gamma ray and the neutron spectrometer. And, oh gosh, so these are the thrusters. So 2 thrusters per arm. The arm has like a shoulder and an elbow so that they can be moved in the right location. And by the way, the video has it wrong. There are 4 thrusters, but only one will ever be on at a time. So we're kind of working with them to fix that, but it's kind of an expensive fix to fix the thrusters. And there it is installed on the left. And then here's what it looks like when it's actually working in a thermal vacuum chamber, this one at JPL. No, actually, I think this is at Glenn Research. We tested them in both places. So it turns out ionized xenon is blue, and so that is what it's going to look like. It's going to look very Star Wars as we go through space, running on noble gas. You have to test that there's no electrical or magnetic interference and the compatibility of all the systems going on. But to do that, you have to put the spacecraft into a Faraday cage that excludes all the external magnetic and electric fields. So what's a Faraday cage the right size for a spacecraft? Well, it's a huge tent of conductive carbon fiber or fabric. So that's our Faraday cage, and that's our spacecraft, and it went in for its testing, which it passed with flying colors. You also have to put it into a thermal vacuum chamber and test the thermal design at space temperature under vacuum. And for that, you need a big honkin' thermal vacuum chamber. See the people? The guy down on the left and the guy up on the left? And that's the bottom of our spacecraft with the adapter ring there, the gold thing. That's how it connects onto both the holder in the shipping container and also the rocket eventually. So that's how you hold it. So we're sliding it in there. This thermal vacuum chamber has a diameter of 25 feet. And to bring it down, they could bring it down to vacuum, the whole thing, after they bolt this giant door in place, and then make it really cold with liquid nitrogen. And it uses so much liquid nitrogen that on the days we were running it, there would be tanker trucks just lined up at the gate of JPL rolling in like one after the other, which was just I don't know, I love that stuff. It just kind of makes it all exciting. And this also has the ability to put solar on the top of the spacecraft, so you can test your spacecraft when it's being baked from the sun on one side and frozen on the other side. Very complicated thermal problem. All of you who do thermal modeling and finite elements, you are needed in aerospace. Here you all saw that in the video, the beautiful wing. And here it is arriving at Kennedy Space Center last summer on a C-17. And that is not the Maxar shipping container. That's the one that we bought for this and 2 other missions. And they had to take it on a test run down at March Air Force Base in California to make sure it fit, because it's designed to fit with just inches on the side. Because the Maxar shipping container actually doesn't fit in a C-17, and a C-17 is the biggest transport plane that the government had to offer us. And so that was an exciting moment that it all fit, and it arrived beautifully, and it's still there. So my final slide here is me on the left. You can see my degaussing wire there. And Brian Bone, our assembly, test, and launch operations manager, on the right under the spacecraft, and he's pointing out with his flashlight the newly installed comms panel on that particular day. So I invite you to follow us on social media and look on our website, and keep your fingers crossed and join us for launch in October. Thanks very much. I'm so happy to answer questions, but I don't know what our timing is.
I think we have a few minutes.
Few minutes? Okay. And of course, if you need to go, please don't feel embarrassed. Any questions at all? Yeah. What are some of the obstacles we are anticipating after launch? Oh my gosh. Okay. The obstacles I fear the most, of course, are the unknown unknowns, because anything could happen at any time. One of the exciting things that happens after launch is there is a 110-day initial checkout, where we're going to test everything that we need to do with the spacecraft in preparation for proper thrusting on our trajectory. So, for example, these missions, the Hall thruster missions, are very different than chemical propulsion. The thruster is on almost all the time, but you always have to check and make sure you actually know where the spacecraft is. So we'll thrust for 7 days at a time, or 6, and then we'll turn it off, swivel it around, and communicate back with Earth, with the Deep Space Network, and say, am I where I think I should be? And how is everything? And then we'll turn it back around and thrust some more. And so I think one of the big obstacles is getting through initial checkout and testing everything that we need to test. During cruise, I'm feeling really good about it. And at arrival, I mean, what are the obstacles? Like getting over your emotional state, I think, is a part of it. But an interesting obstacle, and you can kind of think about this, any of you who are in a field like this, how do you design a mission to answer questions about an unknown body? What is the whole range of things that Psyche could be, permissible by the data that we believe, that would still allow us to answer our questions given the instruments that we have. And so we've tried really hard. We have all these matrices and cartoon pictures and like stories and hypotheses that we think we're going to be okay. But one of the things I'm worried about is that it just ends up being quite different than what we thought, and we get measurements that we can't quite reconcile into answers for the questions we're supposed to answer. But I suppose that's kind of a wussy answer, because in a way that would be fabulous, but it would not be fulfilling what we promised to NASA. So it becomes an obstacle also. Yeah. Yeah.
I'm just wondering what happens to Psyche after it's done.
Yeah, I know. There will be what's called a senior review after we complete. Let us just use the definitive verb tense. There will be a senior review once we complete all of the science that we promised to do, and we will propose to do an extended mission, which would be to cycle down closer and closer to the body and get better and better data. There's no other asteroid going to be near enough us to go visit for any good reason, believe it or not. Like, they're just so far apart. And so some of the student artists on our program thought that was super sad, that this spacecraft that we loved and had nurtured and brought up wasn't coming home. So they made a children's book that's available online about how the spacecraft ends up coming down to the surface of the asteroid, and it's so happy because that's where it wants to spend the rest of eternity. But the truth is, it'll actually, like, unless we actually crash it, it would just be in that final orbit for hundreds of years before it goes unstable on its own, but it'll end up on Psyche. Yeah. Henry, did you have a question?
Yeah, thinking about the science for a minute, you have expectations that you'll be able to infer things like original size if this turns out to actually be a core.
Okay.
And what data might you and other collaborators bring to bear on trying to figure that out? Because I love the idea that it's a core.
Yeah.
I really hope it is.
Yeah.
I'm
I'll repeat the question.
Reimagine,
Yeah. Right. So the question is, would we be able to figure out how big the original body was if Psyche is a partially revealed core? And Penny's saying that she loves the idea that it's a core and she wants to be able to imagine what the parent body was. Probably not. So here's the tricky bit. We puny humans have not actually witnessed giant impacts between planetesimals. We've seen the comet go into Jupiter, kind of a different deal. And so we have all these simulations, and we think we are beginning to understand how the rock could be knocked off of a core. But say Psyche started out like the size of Vesta, because it's sort of the size of Vesta's core. Eric Asfog at University of Arizona says it would take, his numbers vary depending on the model, but let's say between 5 and 11 oblique hit-and-run hits onto that original parent body to knock off the rock without completely destroying the center part. And that in between, there can't be any strikes that really add material. They can't be accumulative strikes. They have to be just destructive strikes. Seems unlikely, right? Another way to do it is to have something kind of the size of the moon hit something sort of the size of Mars, and then the thing that's the moon can actually have its exterior stripped off it as it goes through a strike. And so maybe Psyche, if it's a core, is part of the core of a little planetesimal the size of Vesta. Maybe it's the part of a core of something the size of the moon. Maybe it's a piece of splash off a giant impact onto something the size of Mars. I'm actually not confident we will be able to tell the difference between those states, which is frustrating. But maybe we'll be surprised and something will happen. So this is, like, for all of us scientists, a kind of a cautionary tale. You can't use Occam's razor when you don't have many instances, when it is already a super outlier, not a part of a population, not in a normal distribution. It's an unusual object, and it might have a quite improbable story behind it. Yeah?
I heard an interesting idea that all of the isotopic similarities between the Earth and the Moon could be reconciled if the impactor to the Earth was itself a core and had no silicate mantle. Would it be possible to make a large body, a Mars-sized body, where you had knocked off the mantle, or is that?
That's an amazing idea. So the science that Zach is bringing up is that the isotopic similarities between the Earth and the Moon are quite unbelievable. Like, they seem to be exactly the same material. But the models that say something the size of, make up your body, Mars or whatever, hit the proto-Earth, and spewed off material that became the moon, but the models say that that material would preferentially come from, I believe, the impactor, is that right? Not from the proto-Earth. Therefore, it should have a different isotopic composition than the proto-Earth. Following? So the fact that it doesn't, the fact that it's the same, makes you wonder, how could this happen? So one idea was maybe the impactor didn't have any silicate rock, it was just metal. Maybe it was a fully stripped metal core. Could you make a fully stripped metal core as big as it would need to do this thing? And I would want to, get Eric Asfog to, he's the Mr. Modeler of this process. So I can't give you a definitive answer except to say he's been working on these kinds of ways to strip the rock off the metal now for years and years and years, and none of them are simple. And so I think it would be very hard and maybe impossible. Yeah. But just to add to that, he sometimes has done kind of Monte Carlo series of simulations of creating the solar system through impacts. And in many of them, there is no body like Psyche that results. And in some of them, there's one Psyche, and every once in a while, there's two Psyches. So it's an improbable object. Yeah.
Would you have ways to measure the interior composition or properties of Psyche?
The interior composition and properties of Psyche. Yeah, so the main way that we're going to do that is through our gravity experiment. And so this is done through Doppler. The idea that if something accelerates toward you, the waves are compressed, and if it accelerates away, they are expanded. You can literally do that from Earth using the Deep Space Network and the high-gain antenna on Psyche. So as Psyche is orbiting around, Psyche, the spacecraft, is orbiting around the asteroid, if there's a denser, like say an all-metal part coming up, the spacecraft will be accelerated toward it a little bit, and we'll have a Doppler signal to Earth. And then when it passes it, it'll be decelerated a little bit. And that's the way we build up the gravity field. We're going to get to degree in order 10. And so that combined with topography and composition on the surface, I think we're going to be able to infer something about the interior. You might be interested, in moment of inertia factor, if you're that kind of person. And I would really love to have moment of inertia factor, but I don't think that's going to happen. It's not processing fast enough, and it's too weird a shape, and so we're not going to get that. Anybody else? Oh, thank you. Hello, sorry.
My question is about visible light cameras. Will there be any?
Yeah, the imagers are visible light cameras. Yeah. They're, we call them imagers because it's fancy, right? Also because they're multispectral. Each one has a filter wheel with a set of filters that are designed to look at visible light or NIR spectral ranges that would help us identify certain minerals. And so, but we'll be able to put back together a faux color picture as well. And we've already built the software pipeline such that the images we get down off the Deep Space Network, we're going to put onto the internet free to everyone in the world within a half hour of our receipt. So everyone can see them. You can see the glitches and the things that look like rabbits and everything all at the same time. Yeah. Thank you very much. Oh, one more question.
Maybe it's a political question, but I couldn't understand the physics potential or science potential. We need to read it.
So your question is, why would we need to do this project?
My understanding is there are lots of astrophysical bodies that are roaming around in space. So, what kind of benefits or what kind of new thing that we are trying to extract from this object? Because we are investing lots of money in it.
Right, so the question is, why are we going to this object? There's lots of things out there to look at, and it's very expensive. So I have an approximately 5-hour lecture on this topic, but I will just say, I have a couple of things to say. I think humans, in fact, it's more than I think, I'm convinced that humans explore because we can't help ourselves. We are going to space, whether people want to go to space, everyone wants to go to space, or everyone does not want to go to space. We are going to space, people are going to space. And it's going to happen on government money and private money, as in robotically, and with humans, I think we can't resist. And I think it is a fundamental part of the human soul, and I know it sounds hyperbolic, but I actually do really mean this, to look out over the horizon and find out about things. And I feel like if everybody had that thrill of looking and finding, we would actually be a better society overall. I think if everyone felt they had a sense of agency to go after an unsolved problem, that we would do better. And to see the things that we can do in space inspires us to do better on Earth, and not just in a hypothetical or abstract way, but literally with the technology comes right back to Earth to help, and that is not a stretch. And so there are many of these different reasons why I think robotic space exploration is very important for humans to stay humans. And then to go and say, like, why this body? Because there isn't another one like it. Because it's a new kind of object, because I think it's even more inspiring in curiosity. And I look at the interest. So this is a big, expensive mission, 100%. And I feel the weight and the responsibility of every taxpayer dollar 1,000 times. I really do. But we spend way, way, way more money, many multiples of this, on many other expeditions going to many other places. But I would say that this mission has gotten a lot of attention in the public because it's so new and different. And I think that is a benefit to all of us around the world, to think about something new and different and think about what's positive and practical in this sense, because almost every narrative we have in front of us today is a narrative of guilt and fear. And if we have a society-wide narrative of hope and excitement, I think that's worth everything. Thank you. Such a mysterious object you have here.